The University of North Carolina at Chapel Hill and Cisco are developing a telepresence video wall system for enabling informal conversations between remote coworkers. The goal of this work is to support casual interaction across a 24/7 video wall, in contrast to formal meetings around a table with fixed seating positions. Here we seek to provide a wall-sized display that shows a pleasing panorama overview of the remote room, while simultaneously providing good eye contact for individuals who wish to converse across this video wall. The group has explored multiple methods for achieving these two goals. In the past, the group created a single image that spanned the video wall displays by compositioning images from two sets of cameras. A cluster of cameras created a panoramic image, and a separate array of forward-looking cameras along the wall enabled people to see each other at eye level. However, in practice, there were several problems. First, image segmentation produced artifacts. Having implemented and evaluated current state-of-the-art offline color and depth-based image segmentation algorithms, we found that these approaches were susceptible to errors along the edges of people and objects in office environments. Second, switching between cameras led to a mismatch between the location of people and the panorama and personal camera images that caused a noticeable jump as people approached the displays to speak with one another. In the period January to June 2012, the group focused on an alternative approach for creating a display that provides both a good panoramic overview of the room and good eye contact. The idea, originally proposed by Bill Mockley at Cisco, addresses each of the previous two shortcomings and promises several key benefits. First, image segmentation is no longer required. Depth-dependent perspective uses 3D scene capture with commodity depth hardware instead of compositioning 2D camera feeds. Second, depth-dependent perspective supports eye contact by rendering images with a smooth perspective transition between camera viewpoints, as opposed to an abrupt jump between camera views from the image compositioning approach. Here's how it works. In depth-dependent perspective, each 3D point is rendered from the perspective of a separate camera with a separate camera location. This camera location is determined by a function of the given point's distance to the video wall displays. Here, our goal is to render the scene from a virtual viewpoint that lets people make eye contact for up-close, one-on-one conversations and see the background of the remote room as casual observers when they are engaged in other activities. If the camera's line of sight is far away, then it will closely match the view that a person sees while standing close to the video wall display. And conversely, if the same camera's line of sight is closer to the display, it will more closely match the view as seen by someone standing farther back in the room. The following is a brief illustration of this concept. In traditional computer graphics, 3D models are rendered from the perspective of a camera in 3D space. If a wide-angle panoramic camera is used, people that are looking straight ahead appear to be looking to the side, and vice versa, if a narrow-angle telephoto camera is used, people appear to be looking straight ahead, but the resulting image gives a poor overview of where people are in the room. In depth-dependent perspective rendering, each 3D point is rendered from the perspective of a separate camera with a separate field of view. This field of view is determined by a function of the given point's distance to the video wall displays. If we use a panoramic perspective viewpoint from a distance that is close to the observer on the z-axis, we get an excellent panoramic view of the room, which is good for casual observers but poor for eye contact. If we instead slide this viewpoint further from the user along the z-axis to infinity, we get an orthographic viewpoint that is bad for the casual observer, only showing a narrow telephoto field of view of the back of the room, but good for making eye contact, showing people looking straight on. The group experimented with rendering static pre-scanned 3D models of people as an initial test case. Here, the pre-scanned models are in fact looking straight ahead, like they would be during a conversation across the video wall. However, the rendering approach used greatly impacts how these models appear on the video wall displays. Traditional perspective rendering shows nearby figures looking to the side, which is incorrect and undesirable for maintaining eye contact during one-on-one conversations. While depth-dependent rendering uses a narrow field of view to show the mannequin looking straight ahead when he is close to the display, and a wider field of view to emphasize depth as the mannequin recedes backwards in the room. The UNC-Cisco group's resulting depth-dependent perspective framework is an initial step for achieving the best of both worlds, supporting natural eye contact with a panoramic view of the room. And the group has begun implementing multi-view stereo algorithms for extending this approach for use in real-world dynamic office environments.